Stephanie Arsenault. I am a PhD candidate at Stony Brook University School of Marine and Atmospheric Sciences in Dr. Chen's lab. And today I'll be talking about bay anchovy spawning phenology in a changing Hudson River estuary. I'm going to start with an introduction, talking about a little bit about the species that I'm studying, the ecosystem I'm looking at, and then some important reasons why this type of work is important, and then moving into the data, analytical methods, some preliminary results, and the discussion. So bay anchovy are a small coastal forage fish. They're found along the Atlantic coast of North America, which you can see in the figure there in the black sheeted region. In U.S. waters, they're typically not found north of Cape Cod. So the Hudson River estuary is often considered the northernmost extent of their range. They're found in nearshore coastal, estuarine, and marine waters and can tolerate a broad range of salinities and temperature. They're small, typically less than 100 millimeters fork length, short-lived, only live 2 to 3 years, and are planktivorous. They're prey for economically and recreationally important species such as striped bass and bluefish. They're commonly the most abundant ichthyoplankton in mid-Atlantic bay estuaries, especially during the summer months. And they use the Hudson River estuary throughout their life history stages. So juveniles enter the system in the spring, spawning begins in the summer, the larvae move upstream, and then juveniles move out of the system. And within the Hudson River estuary, they've been experiencing population declines since the 1980s. And in the Chesapeake Bay, they've been experiencing some population declines since the 1990s. A little bit about the Hudson River estuary. It's a partially mixed tidal estuary that stretches 245 kilometers from Troy to the Battery in New York City. It's home to more than 200 fish species, which Katrina highlighted in her talk, and it provides critical spawning and nursery habitat. Like many aquatic ecosystems, it's been impacted by climate change. It has been experiencing decadal scale changes such as warming waters and sea level rise. There's been changes to the precipitation and freshwater flow into the Hudson River. There's a history of pollutants and the invasion of non-native species. And so overall, it's a pretty dynamic ecosystem. And the Hudson River estuary has been a focus of habitat restoration, pollution reduction, fisheries management, and long-term monitoring. So I want to talk a little bit about why this type of work is important. So climate change has impacts on species distribution, habitat availability, and can also affect the phenology of life history processes. So phenology is the changes in seasonal life history events. And spawning phenology in particular can be sensitive to climate-induced environmental variability. And changes in spawning phenology have been widely reported in marine and estuarine waters, and I will go over some examples of spawning phenology changes of key Hudson River fish. And the timing of life history processes can have impacts on fitness, survivorship, recruitment, and future population success. So getting into some of these examples, the first is from Pan et al. In 2023, looking at striped bass spawning phenology from 1974 through 2017. They found that spawning onset and cessation occurred earlier in recent years, and they also found a longer spawning duration. Temperature was an important driver in these changes, and the upper spawning ground was more vulnerable to climate change than the lower spawning ground. So that's shown in the figure there with the red and blue bars. So there's some differences in impacts based on where the striped bass are spawning within the river. Moving on to American shad, which is a species of concern for a lot of people. Chen and Chen in 2024 found that American shad experienced a significantly delayed spawning peak and cessation. So those plots there are showing year on the x-axis and day of year on the y-axis. American shad had an extended spawning season. Higher water temperatures were associated with this earlier spawning onset, and spawning onset and cessation were tied to the size of female spawners. So it's not just abiotic impacts in spawning phenology, there can be biotic impacts as well. And the final example is looking at white perch by Hunt et al. In 2024. They found that the lower extent of spawning habitat is shifting upriver. Egg abundance has declined since 1980 and is currently at historic lows. and egg abundance was tied to temperature, conductivity, river discharge, and some other important variables. And peak spawn timing of white perch has shifted to occur earlier in the year. So these are some key species in the Hudson River that are experiencing shifts in spawning phenology. So the research questions of this larger project are looking at how egg and larval abundances of bay anchovy in the Hudson River have changed over time, what the drivers of those changes are, so looking at biotic and abiotic drivers. Has the spawning habitat extent changed in the Hudson River? So I've looked at that using habitat suitability index models. And then question 4 is looking at has spawning phenology of bay anchovy in the Hudson River changed in response to climate change. So this is the focus of this talk. So getting into the data and analytical methods, all of the data that I'm using comes from the Hudson River Biological Monitoring Program, or the HRBMP. I'm using calibrated bay anchovy egg data from the Yong River survey, and the data was calibrated by Chen et al. In 2023, and it was calibrated to account for survey protocol changes. I'm using data from 1988 through 2017, and I've limited it to day of year 89 to 281, so March through October, when bay anchovy eggs are present in the system. I'm using water quality data from the Water Quality Survey, looking at temperature, dissolved oxygen, and salinity, and I took annual mean values from fixed monitoring stations. And the study area is reduced to the lower Hudson River estuary from the Battery to Indian Point, which is highlighted in the red rectangle, and that's where the primary spawning occurs for bay anchovy, and the extent of the calibrated data. Just a little bit about some environmental variable trends. So these plots are showing annual mean dissolved oxygen, salinity, and temperature. These annual means were estimated by averaging values from depths 1 through 20 meters of these standard water quality stations between March through October when bay anchovy eggs are present in the system. So there's been a significant decline in dissolved oxygen, a significant increase in salinity, and no significant trend in temperature, and this could be because I'm averaging over a large portion of the year. Getting into the data analysis, so I use logistic models to predict the cumulative relative daily catch per unit effort, or PDOY. Onset of spawning is defined as the day of year when 10% of PDOY occurs per year. Peak spawning is when 50% of PDOY occurs each year. Cessation is when 90% of PDOY occurs each year. And then the duration is the time difference between onset and cessation. I use Pearson's product moment correlation to look at the correlation between the spawning phenology metrics, so looking at onset, peak, cessation, and duration. And then I use linear regression models to evaluate if there were temporal trends in the spawning phenology metrics, and then looking at the relationship between phenology metrics and abiotic variables, including temperature, dissolved oxygen, and salinity. I originally considered using GAMs to evaluate the relationship between abiotic variables and spawning phenology metrics, but the effective degrees of freedom were all less than 2, suggesting a linear relationship, and so linear regression models were appropriate to use in this case. Getting into some preliminary results, so I'm going to go through the individual spawning phenology metrics first. So this is the fitted logistic models for estimating the spawning phenology metrics. Each facet is this individual year. The red line denotes the logistic models, the gray bands are the 95% confidence intervals, and the black dots denote observations. So there is some variability year to year. Onset had a significant decreasing trend, suggesting that spawning onset became earlier over the years. So the top plot is year on the x-axis and day of year of spawning. Onset ranged from day of year 154 to day of year 166. So spawning shifted from early June to mid-June. Peak had a significant decreasing trend, indicating that peak spawning became earlier over the years, and it ranged from day of year 173 to day of year 185. Cessation, again, also had a significant decreasing trend, indicating that spawning cessation became earlier over the years. However, there was no significant trend in duration with high variability over the years. So even though spawning onset, peak, and cessation is all shifting, there's been no significant change to the spawning duration. Looking at the Pearson's product-moment correlation, onset was positively correlated with peak spawning and cessation was positively correlated with peak spawning and duration. I won't go into the nitty-gritty of that. And then looking at the relationship between spawning phenology metrics and abiotic variables, onset was negatively correlated with salinity, which you can see in the top plot, and then onset was positively correlated with temperature. So with salinity, a 1 degree change in salinity indicates a 1 day earlier spawning, and then a 1 degree increase in temperature indicates like a 2 day earlier, or earlier onset of spawning. And so this is not really what I was expecting for temperature. I was expecting it to be negatively correlated, especially as the Hudson River is warming, so I'll be digging a little bit more into this. Now going into the discussion. So in general, as a recap, spawning phenology and phenology in general is important for reproductive success and survival. And changes in phenology are often adaptive responses to environmental changes. And previous studies have noted that water temperature is an important driver for fish spawning and changes in phenology. Over time, bay anchovy spawning has occurred earlier in the season, but there's been no significant change in duration of spawning. Spawning onset was correlated to temperature and salinity, and then peak cessation and duration may be influenced by other abiotic variables that I did not consider at the first go-around. Shifts in spawning phenology have been documented for other Hudson River estuary fish, so those 3 examples that I went through at the beginning. Changes to bay anchovy spawning phenology are likely to continue as climate change continues to impact the Hudson River estuary. And these shifts in spawning phenology could lead to a potential mismatch with zooplankton blooms. So spawning occurs in the lower Hudson River estuary, and then larvae move upstream into areas with lower salinity that are rich in zooplankton. And so this shift in when spawning is occurring could create a potential mismatch with these zooplankton blooms. There could be potential implications for other species, as bay anchovy are a primary component of the forage base. They're also experiencing other threats to the population, such as increased predators, decreasing dissolved oxygen, and so looking at changes in spawning phenology, it's really important to try and understand their relationship in the system. So the next steps are to look at additional abiotic factors on spawning phenology. So I originally only considered dissolved oxygen, temperature, and salinity, but I want to look at freshwater flow, sea level rise, and then potentially additional thermal metrics such as temperature minima or maxima. Evaluate whether the extent of spawning habitat has changed. So I've done this with habitat suitability index models, but potentially developing the logistic regression models to look at the changes in the extent, and then building dams to address if there's been changes in bay anchovy egg and larval abundances, and what the environmental drivers of those changes are. I would like to acknowledge Dr. Yong Chen, my advisor, the Hudson River Foundation, Anchovy, which donated the Hudson River biological monitoring data, SOMAS, and then everybody in the lab who's part of the Hudson River research group. And if you want more information about the HRBMP and the Hudson River related work that our lab does, you can visit the QR code. I also manage all of the data requests for the HRBMP data. I'll put in a little plug. So if you have data that you would like to get, you can send me an email. If you want more information, feel free to reach out. Thanks. Yes, Greg.
So the whole mismatch of developing fish and plankton blooms is an interesting idea. It's been brought up, maybe even demonstrated in the Chesapeake Bay as a problem for striped bass. modeling you can do, some way to investigate that question?
I know that there are some shorter monitoring programs that have looked at plankton in the Hudson River Estuary. It's kind of a next step to dig into like what data is available to potentially get at that question. I know it's been demonstrated for other species in different systems, but yeah, I don't know if there's the data available to